the presentation. My name is Arenaz. I am CTO and founder of Apento Solutions. Is the legal name of the company. We are incorporated in Europe, in Spain, and we have been operating in the high-performance computing market for more than 6 years now, introducing this novel technology called Codee. This is the commercial brand. And here, I am glad to be here in Munich presenting a collaborative work done with our colleagues of SiFive, in particular with Vadim Mandelboim, to try to provide results of the first study of what is the impact that Codee, or the benefits that Codee can bring to the RISC-V community, in particular, evaluating this impact on the SiFive LLVM RISC-V development ecosystem. So a bit why RISC-V? RISC-V, you know it, all of you, better than me. I come from HPC, x86, ARM ecosystems, relatively new to RISC-V, and always addressing RISC-V from the software perspective, so trying to help developers writing C++, Fortran applications to run efficiently and faster on any type of hardware. So in particular, for us, RISC-V is, we'll say, yet another platform, but very interesting because it's gaining a lot of traction in the industry. So RISC-V, the benefits provides open, modular, extensible architecture that can be extended to produce chips that can run efficiently specific types of workloads. This means that somehow the chip, the hardware, has built-in instructions that somehow are very beneficial for particular types of applications. AI is a very well-known example. AI will run very, very fast if you make very, very extremely fast small matrix multiplications, for instance. So having this implementation in hardware helps a lot from the software perspective. But the question is, how can we write applications that take advantage of this hardware implemented in silicon? How can we fine-tune the source code or modify the source code to help the compiler to produce more efficient code that takes advantage of these features available in hardware? This is where Codee comes into play. So RISC-V is expanding very rapidly across many industries. We can see it here. And the challenges, according to this collaboration with our colleagues, is that RISC-V somehow needs to compete with very well-known, very well-established hardware ecosystems like x86 or ARM that have very mature software development tools, very mature software development ecosystem that help developers to be very productive in the process of optimizing the source code for a particular type of hardware. Okay? So I would say that the challenge is that it is crucial for the adoption of RISC-V to build a robust ecosystem to help developers developing applications to optimize the code for particular RISC-V cores. So this is where Codee comes into play. As I said, our company was incorporated in 2012, starting from scratch, from leading R&D results in compilation technology, and understanding how we can make the things internally in a different way in order to extract from the source code opportunities for optimization. This means that we can help with vectorization, making use of special instructions, multi-threading, offloading to GPUs, and we have demonstrated this in the HPC market, working with many companies and organizations, leaders in this market. So what Codee provides is, for the first time, it brings the first static code analyzer specialized in modernization and optimization of code. From the user's perspective, those of you that are familiar with secure coding, with static code analyzers to ensure the compliance of your code in regulated markets with MISRA, common weakness enumerations, CSRC. From that perspective, the usability, the user experience of Codee is the same. What is the key difference? Is that whenever we scan the code, we try to look for opportunities in the code that help the developer to understand how to tune the code, how to rewrite the code, so it can run more efficiently and faster on the target architecture. And for this, it's not just about analyzing the code. It's also about understanding what the compiler is doing and being able to provide reports that can help you to understand what the compiler is missing and how you can fine-tune the code for the compiler to do a better job. Okay? So in essence, we help with modernization of code. That means that we can help improve the robustness, stability, maintainability, overall reduce the costs of maintaining the code bases, but also optimization. In HPC, it's about performance, running as fast as possible. In embedded software market, it's a bit more complicated. It's about running faster, but also reducing the code size and being energy efficient. And for this, for instance, taking advantage of special instructions, taking advantage of the vectorization capabilities of the compiler is key for applications to run efficiently on RISC-V cores. So Codee, you have to see it as another piece of software for the software development ecosystem that is not a replacement for the compiler, it's a complement. It doesn't replace the profile of the debugger, it's a complement to it, providing a lot of, I would say, productivity and automating tasks that the developers today need to do by hand, assuming they have the expertise and they have learned to optimize code, which is typically a long-term journey. And also, from day one, Codee is designed to interoperate with IDEs, with CI/CD pipelines to support agile software development, which is key for velocity in software development today. So let's see how Codee is helping in different architectures. These are results published, I think was last summer, in the Intel website, where we demonstrate that for different workloads, Codee can bring or speed up to 18x% faster code of different workloads running on the latest Intel hardware using the latest Intel compiler. And Intel is known for providing a very, very mature software development ecosystem to the developers. So Codee, this demonstrates that Codee is a complement even for mature software ecosystems. How about ARM? Here we can see several results. That is, typically when we talk to customers developing embedded software, they need to use SDKs provided by the vendors. And this SDKs typically use either proprietary compilers or the compiler that is supporting the SDK is based on some GCC version, or the trend today is try to move to LLVM compilers. LLVM compilers are very agile, are providing a lot of optimization possibilities. So here what we are doing is we are comparing what Codee can provide, additional benefits, compared with the maximum optimization level for speed that the LLVM compiler can bring, that the GCC compiler can bring in the latest versions. The latest versions as of November, December, when this study was conducted. And here what we see is that by using the recommendations of Codee, both on ARM and x86 code platforms, we can generate 90% faster code, 10% faster code, 2x faster code, 3x faster code. This depends on the actual software ecosystem and runtime system that you have on your platform. Okay? So how do we prove this? As you know, performance is something you cannot anticipate or prove in advance. So we can, to create the trust on the user and the customer, what we provide is an open catalog of all the more than 80 recommendations related to optimization that Codee has automated today, and that are not automated, essentially, in most of the compilers available in the market. Also, we provide evidences of applications through GitHub open public repositories where you can reproduce the results that we are presenting here. And also, we provide benchmarking capabilities so that you can reproduce these numbers on your own platform to create the trust that Codee will actually work for your workloads used by your developers on your hardware platform. Okay? So the main goal from the technical perspective of this study with SiFive colleagues was to make a similar study for RISC-V for the first time. We had not been doing this before. So essentially, where we focus, as we are targeting embedded software market, we want to evaluate how Codee can help to produce faster and more efficient single-core code. So we are not talking about multi-threading or offloading to GPUs. It's about the code produced by the compiler for serial compilation. How can we make the code run faster? And in particular, we wanted to focus on vectorization. Vectorization is a special type of instruction that has many benefits. It can bring faster code. It's also energy efficient, and it's also exploited or available in most high-performance architectures out there. And the difficulty of exploiting vectorization is not that just only about using the instructions available in the silicon. It's also about how the code, when it runs, is going to make an efficient usage of the memory. So how does it interoperate with the cache memory or with the memory subsystem that is packaged with the hardware? So this is why we selected, for this effort, the vectorization instructions on this system. So the benchmarking machine was a C5 LLVM Linux version 15, C5 P470 out-of-order processor running at 32 megahertz. The latest compiler available at that time, LLVM compiler, so CLAM version 15, cross-compiling for the C5 RISC-V P470 processor. And also with Codee, we are in version 2024.2.5. So it's I would say, quite old. It's only 2023.1 as of September, so 9 months ago. We are evolving very, very fast. But all of the results that you will see here still is possible to reproduce them with the latest Codee version. So for benchmarking, typical benchmarking methodology, average runs of several runs, 5 runs per compiler benchmark, setting the baseline with the maximum optimization level, -0.3, -f fastmath of the compiler for evaluation. And how do we produce the code? We have the original code, and we produce the optimized code in one way. First, using the automated capabilities for Codee to detect opportunities for optimization. And second, Codee also provides auto-fixes. So you can use Codee to actually rewrite the code. You just have to rewrite the code, recompile, verify correctness, and verify the performance gain, if any, that you can get in your platform. And OK, so what are the results? We wanted to use a very simple example that everybody understands, so across many industries and also representative of AI workloads. Here we can see that we have selected 3 different ways of coding the matrix-matrix multiplication. This is intended to show that the same algorithm coded in different ways can bring very significant performance gains or differences in practice when you run it on your target hardware. And here we can see that using the recommendations 39, 43, and 62 of the open catalog, we were able to produce 2.4, 1.5, and even 7.5x faster code running this matrix-matrix multiplication on the SiFive's RISC-V processor. And this is reproducible, again, if you have the target architecture. Where does these benefits come from? Remember, we wanted to evaluate the vectorization efficiency of the vector code produced by the compiler. So we have seen that in one of the versions, in 39, SiFive's Clang compiler failed to vectorize the loop, failed to vectorize the code. So with Codee, you enable new vectorization of new loops that were not vectorized by the compiler. And the other 2 versions, 43 and 62, were actually vectorized by the compiler. So why is it producing faster code? Because with the help of Codee, the compiler is able to produce vector code that runs more efficiently, typically making a better usage of the memory subsystem, reducing cache misses, and making exploiting data locality and temporal locality in your code. And this is the result for a small kernel. We wanted to start simple. But then we wanted to choose a workload that is representative of embedded software development. And we picked up Embed TLS, which is representative of encryption, decryption algorithms, for instance. And here we can see for some of the benchmarks, as expected, Codee will not bring any benefit. Why? Because the compiler is doing a great job. But for other specific workloads, like SHA or like MD5, Codee can bring a very, very significant performance gain. What this means is that with Codee, you can vectorize and run efficiently using the memory, your code on the RISC-V platform. So clearly, it is a complement to the compiler, not a replacement, because it doesn't produce, using Codee, you don't get worse results. You always get the same baseline as the compiler, but also you can improve it. So with this, what we wanted to show is that Codee can be a perfect complement to any SDK for any ARM, x86, or why not, RISC-V software ecosystem. So conclusions, and with this I try to convey the message. Okay, RISC-V is here to stay, but it seems that it needs to be competitive. So it needs to provide a mature SDK with regard to ARM and x86 well-established ecosystems. Second, LLVM seems to be the adoption. We see major vendors, Intel, NVIDIA, AMD, adopting LLVM compilers, even discontinuing the development of proprietary compilers. So LLVM seems to be the way to go from the compiler perspective. But again, with Codee, we are showing that LLVM is great, it's a great compiler, but the developers can do a lot of work to help the compiler to produce more efficient, faster code. And with Codee, we bring for the first time an automated way and a solution to help developers to modernize the code and optimize the code for different targets and different objectives. And here we are demonstrating for the first time that this is also valid for RISC-V ecosystems, where we see a lot of systems, hardware systems growing and being adopted in the market. So this shows that Codee makes the upstream LLVM plus RISC-V ecosystem even better than it is today. So a perfect complement for any SDK for developers. As future plan, we plan to continue the collaboration and try to make more comprehensive studies of different workloads tailored for different markets or applications. And that's it. So thank you very much for your time. I hope you find it interesting. I will be around here all day long. I'm very happy to jump into any conversation. Thank you.